block diagram, we can see it's a message source. First block is the message source. And here we have a transmitter. Message source is followed by a transmitter. And we have a channel. And we have a receiver. And from the so here we have a message signal, message source. The first block is the message source. Board clear or no? Okay. So we have a message source followed by a transmitter, followed by a channel, and at the end we have a receiver. So the output of a message source is MI. And output of transmitter is SI of T. And output of channel is X of T. And the output of receiver is nothing but M cap, which is the estimate of this MI. Estimate of digital communication the block diagram first block diagram is message source. This message source transmit one symbol T seconds one symbol so transmit the message source block it transmits one symbol every T second it transmit one symbol. The symbol here it belongs to an alphabet M. This symbol here it belongs to an alphabet M and M can take values M1, M2, etc. M. So the transmitter message source transmit another one symbol per T second. Every T second it will transmit one symbol. And the symbol is nothing but it's an alphabet which belongs to capital M normal secular alphabet. The symbol which we are transmitting. That is message source emit symbol it is an alphabet and it is in the range M1, M2, etc. to M. Here binary symbols the zeros and ones one. As we already know, binary symbol is zeros and ones. So this is about the message source. Message source transmit a symbol MI, that is every T second MI signal symbol message source transmit. This MI I can here take values from 1, 2, 3, etc. to capital M. It is symbol is nothing but an alphabet M, and here a message source is transmitting a symbol MI, and this MI I can take values from 1, 2, 3, etc. to capital M. And binary symbols are zeros and ones one. Now we will go to the transmitter side. Here, in the transmitter side, the message probabilistic in nature. In the transmitter, the MI message, incoming message, probabilistic in nature. With probabilities or prior probabilities P1, P2, etc. PM. അതായത് ട്രാൻസ്മിറ്ററിൽ വരുന്ന മെസ്സേജ് സിഗ്നൽ എന്ന് പറഞ്ഞാൽ ഇറ്റ്സ് പ്രോബബിലിസ്റ്റിക് ഇൻ നേച്ചർ ആണ്. ആൻഡ് ദ പ്രയർ പ്രോബബിലിറ്റീസ് എന്ന് പറഞ്ഞാൽ P1, P2, P3, etc. PM. That is for MI, M1, P1, M2, P2, for etc. M cap, small m, capital M എന്നുള്ള സഫിക്സ് അല്ല, ആ സഫിക്സ് ക്യാപിറ്റൽ M എന്നുള്ളതിന് പ്രോബബിലിറ്റി PM ആണ്. ഇത് പ്രോബബിലിസ്റ്റിക് ഇൻ നേച്ചർ ആയതുകൊണ്ട് തന്നെ ഇറ്റ് ഹാവ് പ്രയർ പ്രോബബിലിറ്റീസ് P1, P2, P3, etc. PM. That is incoming വരുന്ന സിഗ്നലിന് it has prior probabilities like P1, P2, P3, etc. PM. So the a priori probability for this information source, for the message source. can be denoted as Pi. Pi is nothing but P of Mi. അതായത് മെസ്സേജ് സോഴ്സിന്റെ പ്രോബിലിറ്റി. അതായത് മെസ്സേജ് സോഴ്സ് എന്ന് പറഞ്ഞാൽ മെസ്സേജ് സോഴ്സ് എമിറ്റ് ചെയ്യുന്ന സിമ്പലിന്റെ പ്രോബിലിറ്റി ആണ് PA. That is a priori probability for the information source is nothing but Pi, which is equal to P of Mi. 3 clear ആണോ? So P of Mi. So P of Mi it is nothing but 1 by M. For I equal to 1, 2, 3, etc. M. So message source or symbol every t second or symbol emit output that is given to a transmitter. A transmitter is a transmitter message it's a probabilistic in nature. So it have a prior probabilities of P1 corresponding to M1 symbol and P2 corresponding to M2 symbol and PF corresponding to MM symbol. So the a priori probability for the information source, that is for the message source, is given by Pi, and Pi is nothing but P of Mi, and which is equal to 1 by M. For I equal to 1, 2, 3, etc. M. What does the transmitter do? The transmitter takes the message source output from output, that is the message source in the output Mi. So the transmitter, what it do is it takes the message source output Mi and code this Mi to distinct signal Si of t. The transmitter na cheyacha ee message source in the output title Mi na code to distinct signal Si of t at code, and output of the transmitter we get Si of t. And this Si of t is suitable for transmission over the channel. Is that clear? But this transmitter takes this message source output Mi. This Mi transmitter will code to Si of t. That is digitally we communication channel transmit a suitable form like a code. This is nothing but Si of t. The transmitter takes the message source output Mi and it code into the distinct signal Si of t. Transmitter Mi code to the distinct signal Si of t, and this signal Si of t is suitable for transmission over the communication channel. 3 clear ആണോ? സ്പീഡ് ആവുന്നുണ്ടോ?
ക്ലിയർ ആവുന്നുണ്ട്.
സ്പീഡ് ഉണ്ടോ?
ഇല്ല.
And the signal Si of t the signal Si of t has a duration t seconds. We are transmitting signal Mi, like the symbol Mi we are transmitting every t seconds. So the signal Si of t has a duration t seconds, and it is importantly a real valued energy signal. This Si of t it's a real valued energy signal. This Si of t is nothing but a real valued energy signal. So this energy can be denoted as Ei. It's nothing but 0 to t, as the signal has duration of t seconds. So this energy can be calculated. Si of t is nothing but real valued energy signal. So energy can be calculated over the duration 0 to t, as the symbol has a duration of t seconds, into energy Si square of t dt, where I equal to 1, 2, 3, etc. M. So, talking about this Si of t has a duration of t seconds. Si of t is nothing but a real valued energy signal, and so the energy can be calculated by the equation Ei. Ei is nothing but equal to 0 to t, as the signal has a duration of t seconds. So 0 to t Si square of t dt, where I equal to, here I can take the values 1, 2, 3, etc. to up to m. This is about the transmitter side. So we have completed the transmitter side. Now we will move on to the channel. That is, we will study about the channel assumption. What are assumptions are taken with respect to the channel? The channel is assumed to have two characteristics. The channel is assumed to have two characteristics. One is the channel is linear and is wide enough. The channel is linear and is wide enough to have to accommodate the signal SI of t. SI of t in the signal accommodate channel linear and it's wide enough. It can accommodate the signal SI of t with no or negligible distortion. Wide enough to accommodate. So, with no distortion. Each channel characteristics it have two cara. One is it is linear and wide enough. It can accommodate the signal SI of t which is coming from the transmitter and with no or negligible distortion. Without distortion, it can accommodate the signal SI of t. This is channel first cara. And second is that the channel noise, that is W of t. Channel noise W of t is a zero mean. This noise has zero mean and it's a wide Gaussian noise. W of t is a wide Gaussian noise. That is, the channel have a noise W of t is a zero mean wide Gaussian noise. So channel have two cara. First cara is linear, wide enough. It can accommodate with no distortion. That is SI of t with no distortion. It can accommodate as it is a linear and wide enough for accommodation. And next the channel noise is W of t and is a zero mean and wide Gaussian noise. So considering the channel as additive wide Gaussian noise and received signal. So we assume that the noise W of t is additive wide Gaussian noise. As per the second cara or characteristics of the channel, we assume that the noise is additive wide Gaussian noise. So we can write or we can express the received signal as x of t. The channel receiving the signal, the channel output x of t can be represented as x of t is nothing but SI of t plus this additive wide Gaussian noise W of t. This channel receiving SI of t, it can accommodate SI of t as it is wide and linear and with no distortion or negligible distortion. And next cara the noise is additive zero mean wide Gaussian noise. So assuming the channel noise is additive wide Gaussian noise, received signal x of t can be written as SI of t, which is the incoming from the which is the output of the transmitter plus this channel noise, which is additive wide Gaussian noise. So x of t is nothing but SI of t plus W of t, and here t is between 0 and capital T, and I equal to 1, 2, 3, etc. Here the t can take values between 0 to t, as the symbol has a duration of 0 of t seconds or t interval duration. The signal can, the value small t can take between 0 to t. That is symbol duration is between 0 to t. So the value of this t can take between 0 to t. And I here varies from 1, 2, 3 to m. 3 clear ആണോ? എല്ലാവർക്കും ക്ലിയർ ആണോ? സനില, പാർവതി, ഓക്കെ. രോഹിത് ക്ലിയർ ആണോ? So this model, that is this channel model, it provides a basic design for optimum receiver, which will study receiver. So this channel model provide a basic design for optimum receiver, for which we use geometrical representation of a set of transmitted signal Si of t. This optimum receiver we will study in this module later. So this channel provide a design of optimum receiver. Now we will go to the receiver side. This is our receiver. Receiver and the output is M cap. This is nothing but estimate of Mi. So this receiver, it has a task of observing the received signal x of t. Receiver like a signal it's x of t. So it have a task of observing the signal x of t for a duration of t seconds. And it makes the best estimate. Best estimate of transmitted signal Si of t. So the receiver, what it do is it observe the incoming signal x of t for a duration of t seconds. That is, the receiver has a task of observing the received signal. Received signal receiver x of t. So the receiver has a task of observing the received signal x of t for a duration of t seconds. T second duration it have a task of observing observing. That is x of t receiver t seconds observing. And it make the best estimate of transmitted signal Si of t. Si of t is the best estimated receiver find you. But due to the presence of channel noise, the decision making by the receiver decision making it is statistical in nature. Sometimes it may go wrong. Right? Due to the channel in the noise, noise in the channel, decision making by the receiver is statistical in nature. So, and the result that the receiver will make occasional error in them. That is, sometimes it may go wrong or error may occur due to the statistical nature of the receiver. So, in the overall view of receiver it have a task of observing the incoming signal x of t over a duration of t seconds, and it make the best estimate of the transmitted signal Si of t. Transmitted signal Si of t. So it make the best estimate of this Si of t. And due to the channel noise, the decision making process in the receiver it have a statistical nature, and it create occasional error while making decisions. So, is it clear or no? And so, due to the occasional error or due to the design of the receiver, we have to design a receiver so as to minimize the average probability of simple error. So we have to design a receiver that will minimize the average probability of simple error. The simple error is defined as PE. The average probability of simple error is defined as PE is nothing but summation I tends to 1 to m PI into probability of m cap is not equal to mi by mi. This is the average probability of simple error. Simple error, the average probability is denoted by PE, and it's nothing but summation I equal to 1 to m PI of probability of m cap, which is the m cap is the estimate, which is not equal to mi divided by mi. Where mi is the transmitted symbol, So MI എന്ന് പറഞ്ഞാൽ നമ്മൾ ട്രാൻസ്മിറ്റ് ചെയ്യുന്ന സിമ്പൽ ആണ്. MCAP is the estimate of the estimate produced by the receiver. MCAP is the estimate produced by the receiver, and this P of is nothing but this P of MCAP, which is not equal to MI by MI, is nothing but conditional probability. This is the conditional probability, or conditional probability, or conditional error. This is the conditional error. So we have to design a receiver which will minimize the average probability of simple error PE. So equation for PE എന്ന് പറയുന്നത് ഇങ്ങനെയാണ്. Here MCAP is the estimate of the simple MI ആണ്, and MI is the transmitted signal from the message source ആണ്. So this receiver, that is this design, is said to be optimum, or optimum receiver. That is optimum in the minimum probability of error. So we have to design a receiver that will minimize the average probability of error. Probability of error na average probability of error na minimize ചെയ്യുന്ന രീതിയിൽ we have to design a receiver, and that receiver is said to be optimum, optimum in the minimum probability of error. That is optimum in PE. This is about the receiver. Is clear ആണോ? Clear ആണോ?
Clear.
അതായത് റിസീവർ ആണ്. റിസീവർ സൈഡിൽ നമ്മൾ പറഞ്ഞിട്ട് റിസീവറിന്റെ ടാസ്ക് എന്താണെന്ന് വെച്ചാൽ റിസീവർ ഹാസ് എ ടാസ്ക് ഓഫ് ഒബ്സർവിംഗ് ദ സിഗ്നൽ എക്സ് ഓഫ് ടി ഒബ്സർവ് ചെയ്യും ആൻഡ് മേക്ക് ഡിസിഷൻ ബേസ്ഡ് ഓൺ ദ ഡിസിഷൻ മേക്കിംഗ് ഡിവൈസസ്. പക്ഷേ ഡിസിഷൻ മേക്കിംഗ് ഡിവൈസസിന് സ്റ്റാറ്റിസ്റ്റിക്കൽ ഇൻ നേച്ചർ ആയതുകൊണ്ട് ഇറ്റ് ക്രിയേറ്റ് ഒക്കേഷണൽ എറർ അത് ക്രിയേറ്റ് ചെയ്യും. So in order to minimize this occasional error എന്ന് പറഞ്ഞാൽ it's due to the symbol error ആണ്, പിന്നെ conditional error കൂടി occasional error ആണ്. So in order to minimize the average probability of error, that is PE, we have to design a receiver, that is optimum receiver, which we will study later. So optimum, this receiver is said to be optimum in the minimum probability of error. And here we can model the channel. Channel എങ്ങനെ model ചെയ്യുന്ന വെച്ചാൽ here we have a transmitted signal. Here we have wide additive, wide Gaussian noise, and output is nothing but the received signal. So the channel can be modeled like this. That is transmitted signal plus additive wide Gaussian noise is nothing but received signal x of t. Si of t plus W of t. And Si of t plus W of t is nothing but x of t. Now we will learn about the signal space concept. Signal space concept is the same. It is a key to analyze, understand the performance of digital transmission. Digital transmission understand ചെയ്യാനും analyze ചെയ്യാനുള്ള അതിന്റെ performance analyze ചെയ്യാനാണ് ഈ signal space concept യൂസ് ചെയ്യുന്നത്. Signal space concept. And we can define inner product. ഒരു signal space concept important terms ആണ് inner product എന്ന് പറയുന്നത്. Inner product വരാൻ പോകുന്ന normal product term. So inner product എന്ന് പറഞ്ഞാൽ we can estimate the inner product, or we can calculate the inner product of two complex valued signal. Two complex valued signalന്റെ inner product എങ്ങനെ calculate ചെയ്യാം. So consider two complex valued signal x1 of tu and x2 of tu. That will be the two complex valued signal. And the inner product is given by x1 of t, x2 of t. This is the notation for inner product. That is the triangle bracket. ഈ ബ്രാക്കറ്റിനുള്ളിലാണ് നമ്മളെ 2 കോംപ്ലക്സ് വാല്യൂഡ് സിഗ്നൽ is x1 of t into x2 of t. It's nothing but minus infinity to infinity x1 of t into x2 conjugate of t dt. ഇതാണ് നമ്മൾ inner product of 2 complex valued signal. The term inner product എന്ന് പറഞ്ഞാൽ of 2 complex valued signal x1 of t and x2 of t is nothing but x1 of t into x2 of t minus infinity to infinity x1 of t conjugate of x2 of t dt. Like this, we calculate the inner product. And these two signals, these two complex valued signals are said to be orthogonal. This perpendicular to each other. These two complex valued signals are said to be orthogonal if this inner product value, zero aambana, these two complex values are said to be perpendicular. That is orthogonal. These two complex value signal x1 of t and x2 of t are said to be orthogonal or perpendicular to each other when this inner product value is equal to 0. We calculate the inner product value 0, we can say that these two complex valued signals are orthogonal or they are perpendicular to each other. Clear or no? Clear or no?
Clear on.
Tanila, clear or no?
Miss, clear on.
So, time. So tomorrow we are going to learn about the geometric representation of signal.